Namaste dosto. Imagine holding a perfectly round ball, maybe a cricket or that shiny new marble you got recently. Have you ever stopped to think what makes its shape so special? Today, we're diving into the world of spheres, one of the most symmetrical and fascinating 3D shapes in geometry. Now, a sphere is unique because every point on its surface is exactly the same distance from its center, like a magical invisible string holding each spot tight and equal. This distance is what we call the radius, usually denoted as r, and the very center point, we label it O, simply because every center deserves a name. Another cool fact, a sphere doesn't have any edges or vertices like cubes or pyramids. It's all smooth and curved. How do we create a sphere? Imagine taking a semicircle that's just half a circle and spinning it all the way around its diameter. When it completes one full spin, bingo, you get a sphere. And here's an interesting little geometry secret. Any slice you make through the center of that sphere will always be a perfect circle. And all these circular slices share the same radius, r. Isn't that shape symmetry amazing? Picture this in your mind or on the slide, a sphere labeled with center O and radius r, helping you see how this shape is perfectly balanced in every direction. Alright, now that we have a solid understanding of what a sphere really is, let's move ahead to explore its surface area. What exactly covers this round shape on the outside? Stay tuned. Welcome back, friends. So, we know what a sphere looks like and how it's formed. Now, let's talk about its surface area, but specifically the curved surface area, since a sphere only has a curved surface. Simply put, the surface area of a sphere is the total area that covers its outer shell. Think about wrapping the entire sphere with a thin sheet of paper. The amount of paper you'd need to cover it perfectly is the surface area, which we denote as A. Now comes the important part, the formula. The total surface area of a sphere is given by the famous formula A equals 4 pi r squared. Let me say that slowly. A is equal to 4 times pi times r squared. Here, r is the radius of the sphere, the distance from the center O to any point on the surface, and pi is approximately 3.14. This formula tells us something interesting. The surface area increases with the square of the radius. So, if you double the radius, the surface area becomes 4 times as big. This is an example of what we call a quadratic relationship. Picture the diagram on your screen. A sphere with the radius marked, and a curved outer surface shaded to remind you that it's this curved skin we are measuring. This surface area formula simplifies many complex problems in physics, engineering, and everyday life. Before we jump into how this formula is derived, let's pause for a quick mental check. If you triple the radius of a sphere, by what factor does the surface area increase? Exactly, 9 times. Because 3 squared is 9. Shabash. Ready to see how this formula comes to be? Let's break it down next. Arey wah. Now, here's an elegant way to understand where 4 pi r squared really comes from by thinking about hemispheres or half spheres. Imagine cutting a sphere right through its center. What do you get? 2 equal halves called hemispheres. Each hemisphere has a curved surface area of 2 pi r squared. That's 2 times pi times r squared. So, if one hemisphere covers an area of 2 pi r squared, then 2 hemispheres, which make up the whole sphere, will have a total surface area of twice that. Mathematically, that's 2 times 2 pi r squared, which equals 4 pi r squared. Here it is again. Surface area of sphere equals 4 pi r squared. This derivation relies on the idea that the curved surfaces of the 2 hemispheres join smoothly without any gaps or overlaps, making the total curved surface area seamless. On the slide, you can see the sphere broken into 2 hemispheres, each with their own radius labels, helping you visualize how the curved areas add up. By decomposing the sphere into simpler shapes, we can understand and remember this formula more easily. Isn't that a neat trick? Now, stick around as we discuss how units work with surface area, an important topic often overlooked. Excellent beta. As we work with surface areas, always remember, we are measuring a two-dimensional extent on a three-dimensional object, which means units must be squared. For example, if the radius is measured in centimeters, the surface area units will be centimeters squared, written as cm squared. The same goes for meters squared or m squared, depending on the system you use. The dimensional formula of surface area is L squared, that's length squared, since area measures how much length times length covers the surface. Let me make this clearer with an example. Suppose we scale the radius of a sphere by a factor k. Then the surface area scales by k squared, because surface area depends on radius squared. On your slide, there's a chart comparing spheres with radii. 2r and 3 are showing how their surface areas increase dramatically. 1, 4, and 9 times the original area, respectively. This visual really drives home how quickly surface area grows with radius. So, it's crucial to keep track of units and scaling. It helps avoid common mistakes in problem solving. Now for a practical example. Let's calculate the surface area of a real spherical object. Ready? Great! Here's a solved example to put all this formula magic into practice. Suppose we have a spherical ball with a radius of 7 centimeters. Our task is to find its surface area using the formula we learned, A equals 4 pi r squared. Step 1. Substitute r equals 7 into the formula. So, A equals 4 times pi times 7 squared. 7 squared is 49. So the equation becomes 4 times pi times 49. Step 2. Calculate. Multiplying 4 by 49 gives 196. So, A equals 196 times pi. Now, substituting pi with approximately 3.14, we get A equals 196 times 3.14, which equals about 615.44. Therefore, the surface area is approximately 615.44 centimeters squared. Always remember to check your units. Since radius was in centimeters, surface area must be in centimeters squared. And verify if the result makes sense with the size of the sphere. On your slide, you'll see a spherical ball with the radius labeled to help you visualize the problem. Now, a quick checkpoint. If the radius were doubled to 14 centimeters, what would the surface area roughly be? Yes, it would be 4 times 615.44. or about 2,461.76 centimeters squared. Excellent. To wrap up today's session, let's recap what we've learned about the surface area of a sphere. First, the main formula, total surface area of a sphere equals 4 pi r squared. Second, for hemispheres, the curved surface area without the base is 2 pi r squared. With the base included, it's 3 pi r squared. Remember these key ideas. Surface area depends on the radius squared. That means it increases quadratically as the radius grows. Also, spheres are unique because they have no edges or flat faces, only one smooth curved surface. Always keep your units squared when dealing with surface area, like centimeters squared or meters squared. And finally, understanding spheres by dividing them into hemispheres makes it much easier to grasp and derive surface area formulas. Now, a quick quiz for you. If a hemisphere's curved surface area is 140 cubic centimeters, oops, that's not possible. Surface area is not in cubic units. So, catch the trick there. Surface area will always be in square units. That's a critical fact to remember. Keep practicing these concepts and soon you'll find calculating areas of spheres quick and enjoyable. Shabash. Until next time, remember, geometry is around you everywhere, from the cricket ball to the planets. Keep exploring and never stop being curious.